All right. Hello, everyone, and welcome back to Psych 3530. This week, we are discussing the beginning of multi group designs. This will include one way as well as repeated measures, what we call ANOVA statistics. Specifically, this week, we're going to start off with the one way ANOVA and what kind of designs, research designs, require this particular statistic called the one way ANOVA. So, a one way ANOVA is used to determine whether there are statistically significant differences between the means of three or more independent or unrelated groups. So, literally, the only difference between a one way ANOVA and a t-test is that instead of comparing group 1 versus group 2, like a t-test, in an ANOVA, we are comparing group 1 versus group 2 versus group 3 or more, right? We could have group 4, we could have group 5, we could have group 6, so on and so forth, but at least 3 groups. That's it. That's the only difference. And in particular, a one-way ANOVA compares independent groups. So it's analogous to an independent t-test in that the groups differ, right? We have a group of one people who are different people, right, in a different experimental condition from the second group, who now, in the case of a one-way ANOVA, are in a different experimental condition from the third group. So if we're interested in the effectiveness of a medication, right? That's our research question. Does this medication, reduce symptoms? If we have group 1 who gets none of the medication and group 2 who gets 10 milligrams and that's it, then what we have is an independent t-test. Because we have two groups that are independent of one another, right? Group 1 that gets 0 milligrams is a different group of people from group 2 who gets 10 milligrams. So if we add a third group, if we add a 20 milligram group, then we need a different statistic. We need to use the one-way ANOVA to compare the effectiveness of this medication across 3 groups. That's it. So from a design perspective, it's the same thing as an independent t-test. We have independent groups that each receive a different treatment or a different condition of the independent variable. If there are 2 groups, we use an independent t-test. If there are 3 or more groups, we use a one-way ANOVA. Now, one point I want to make that we're going to come to later when we talk about the statistics is that the ANOVA is considered what's called an omnibus test, meaning the test itself will tell us whether or not the groups differ from one another. But then we have to follow that up, if it's significant, with what are known as post hoc tests. Post hoc meaning like after the fact. Post hoc tests will tell us specifically which groups differ from which other groups. So let's sort of make that concrete. Let's make that real with our example here. If I were to conduct an ANOVA on data that I collect from these 3 groups on the effectiveness of a medication, and let's say the ANOVA is significant, that means the ANOVA tells me that somewhere in this comparison of 3 groups is a significant difference. The problem is the ANOVA doesn't tell me, is it group 1 versus group 2? Or is it group 1 versus group 3? Is it group 2 versus group 3? Or is it all 3 groups compared to each other? Like, where exactly does the difference exist? The ANOVA tells me that there is a difference, but it doesn't tell me where the difference is. So if we have a significant ANOVA, Then we have to run some additional tests. We'll see examples of this. Those additional post hoc tests will do individual comparisons between all of my groups such that I know exactly what's going on. So, in this sense, the one way ANOVA, when it's significant, is a bit more complicated because it requires this sort of additional set of tests that will tell me where the difference lies. So again, I'll sort of summarize that quickly. A one-way ANOVA will tell me if a difference exists between my three groups, but the one-way ANOVA will not tell me where that difference exists. If the ANOVA is significant, then we have to conduct post hoc tests, and those post hoc tests will do individual comparisons between my groups such that I know exactly where the difference lies. Okay. So now we're going to talk a little bit about the theory behind the statistics of a one-way ANOVA, and then we're going to do an example. So ANOVA, this acronym, ANOVA, actually stands for analysis of variance, because what an ANOVA does is compare the different sources of variability within an experimental design. And variance is broken down into two important types: within samples or within subjects variance. This is the variability within a single condition. So basically, if you're in the 10 milligram group, if we're just looking at the 10 milligram group, how much do the 10 milligram people vary against each other, right? Within their own sample, within the condition of 10 milligrams, how much do they vary? And then how much do the 0 milligram people vary against each other within the 0 milligram group and then the 20 milligram group? So within samples or within subjects variance is how much do individuals vary around the mean of their experimental condition. I'm going to keep coming back to this example. Sorry for clicking backwards. So we have three groups here: 0 milligrams, 10 milligrams, 20 milligrams. Within subjects variability, ask the question, okay, people that are given 0 milligrams of the medication, how much do they vary on the effectiveness of this, right? And this comes down to something that we would call the placebo effect, right? That people are going to change just from taking a pill, even though that pill has no medication in it. So how much variability is there within this group? Then how much variability is there within group 2? Then how much variability is there within the effect of the medication on group 3? That's within samples variance. Between samples variance says how much does group 1 differ from group 2 and differ from group 3? So this is variance between all the conditions. And what an ANOVA does is it compares the amount of between groups variability to the amount of within groups variability. Because if we're doing an ANOVA, we're asking the question, does amount of medication cause these groups of people to differ from one another? That's the question we're asking. In this example, does the amount of medication cause these three groups of people to begin to differ from one another? That's our between samples variance, right? Is the 0 milligram group, different from the 10 milligram group and different from the 20 milligram group on symptoms, right? Whatever our outcome is. So we take that variance, how much do our groups differ from one another, and we compare it to the difference of individuals within the same group, within group variance. So we have two sources of variability. This is going to become a little more clear in a second when we get some visuals and we do some examples. But just keep in mind, between samples variance is, do my conditions differ from one another? And then within samples variance is, do individuals within a condition differ from other individuals within their condition? Ideally, we want high between samples variance, because that would mean the medication is working, right? Our manipulation of the world, our independent variable, is doing something, right? If my 0, my 10, and my 20 milligram groups differ from one another. So we want lots of between samples variance, but we want very little within samples variance. We want our individuals within our samples to be homogeneous, to look the same. So in conducting an ANOVA, we make 3 assumptions about the data. We're not really going to get into what happens if we violate these assumptions. That can happen, and there are steps we take to sort of mitigate the effects of these violations. But for now, for our basic introduction to an ANOVA, we're going to just introduce these assumptions, and we're going to assume that these assumptions are met. So the dependent variable, so our outcome, so in the case of our example, our symptoms, or the effectiveness of the medication, the dependent variable is normally distributed within each group, that there's homogeneity of variance, meaning that all 3 groups sort of have similar levels of variability, and that my 3 groups are independent of one another. There's independence of observations. So these are 3 assumptions of the statistic. They can be violated. If they are violated, then we have to sort of make amends. We have to make some adjustments, but we're not going to worry about that right now. We're just going to move forward, assuming that we have met these criteria. Okay, so to sort of summarize once again, our t-test is a situation where we have one dependent variable, one independent variable, but that independent variable has 2 levels. So 0 versus 10 milligrams, versus a one-way ANOVA, where we have a test statistic, which we call an F, where we have 2, or I'm sorry, that should say more than 2 levels of the independent variable. So 3 or more levels of the independent variable. So 0 milligrams, 10 milligrams, 20 milligrams, 30 milligrams, 40 milligrams. 3 or more levels of the independent variable. So this sometimes begs the question, if we have 3 independent groups, sorry, I'll go back here again. If I have 3 independent groups, why don't I just run a bunch of t-tests, right? Because I already have a tool in my tool bag that enables me to compare group 1 to group 2, right? I have a t-test. I can use that same tool to compare group 1 to group 3, a t-test. I could use that same tool to compare group 2 to group 3, a t-test. Why don't I just do a bunch of t-tests instead of having this other statistic? The reason why we don't run multiple t-tests is called type 1 error, or false positive error. So every time we run a statistic, it's possible that our conclusions are incorrect. Now, why our conclusion, why the results might be incorrect, is sort of a complicated thing to discuss. It has to do with really a lot of details about statistics, about probability, about really even philosophy, and the philosophy of science. Think about it this way. Let's say that I have this 3 groups of people who take the medication: 0 milligrams, 10 milligrams, 20 milligrams. And let's say that in reality, the capital T truth of the world is that my medicine is shit. It does nothing. It's fake, right? I'm literally trying to scam people. It's snake oil. My medicine does nothing. Well, it's possible that I could collect data and run the statistics, and because of either random fluctuations in sampling error or because of me manipulating things on the back end, I could make it look like a significant result. I could make it look like the medicine works. Right? That's possible. And in fact, the probability of that happening by chance is exactly alpha. So if alpha is 0.05, then there's a 5% probability that I find a significant result that is incorrect, that doesn't actually exist in the real world, in the capital T truth of the world. So the capital T truth is that the medicine does nothing. But because of random sampling error, because of experimental error, because of the fact that people are messy, right? Collecting data from humans is a difficult and messy process. There's a 5% chance that my conclusion that the medicine works is actually an incorrect conclusion. So that chance is always alpha. That's actually what alpha means. If alpha is 0.01, then we reduce our chance. It's actually a 1% chance because it's a more stringent hurdle to jump over. So if every time I run a statistic, if alpha is 0.05, I have a 5% chance of making a decision error, making a type 1 error, then every time I run a test, I inflate my rate of that error. So if I run 1 t-test, then I have a 5% chance. If I run 2 t-tests, then I have a 5% and a 5% chance. If I run 3 t-tests, I have a 5%, 5%, 5% chance, right? Every time I run a test, I inflate the probability of making a decision error. And this is fine. This is the way statistics works, because statistics can only approximate the world, right? We can only gather samples of data and then make assumptions, make generalizations about the world. So we accept this level of risk and we mitigate this level of risk. And we mitigate this level of risk by developing the ANOVA, such that we now have a test that can do a bunch of comparisons at once, and so keep our risk at only 5% because we run one ANOVA statistic rather than running multiple t-tests. So that's really why we have the ANOVA. If this error rate didn't matter, if it wasn't a concern, we would just run a bunch of t-tests. We would never need the ANOVA. But we need the ANOVA because the ANOVA is a single test that we can run. So it keeps our error rate right where we want it at alpha, and it does not inflate our error rate by forcing us to run multiple t-tests. Okay. So we're finally going to get to the meat and potatoes of the F statistic. The F statistic is a comparison of, like I said, between groups variance with within groups variance. In fact, it's a ratio. So F is equal to basically the between groups variance divided by the within groups variance. And we want a lot of between groups variance. We want our numerator to be large, so we get a large F, just like with a t-test. And we want our within groups variance to be small, our denominator, so that we get a large F, just like with a t-test. Now we can visualize the difference between our variances with this figure down here at the bottom. So again, I want us to imagine that we have on the left here the distribution of the 0 milligram group, right? This is on our x-axis, we have sort of group 1, group 2, group 3, right? 0 milligrams, 10 milligrams, 20 milligrams. And so we're looking at the frequency of the effectiveness of the medication. So our y-axis is frequency. Along our x-axis, we see our 3 groups, and we're measuring the effectiveness of the medication. Within groups variance is how much people vary who are all in the 0 milligram group, right? So these are all the people who over here on the left who got 0 milligrams of the medication. Here's their average of their symptoms, let's say. And some people who took 0 milligrams have, maybe fewer symptoms. Some people have more symptoms. Then we have the 10 milligram group. Some people have fewer symptoms. Some people have more symptoms. Then we have the 20 milligram group. Some people have, right, more or fewer symptoms than everyone else. There is variability within each treatment group. Right? People who take 10 milligrams, some of them do amazing. Some of them do okay. Some of them do poorly. Right? There's variability in the medication. If you have high blood pressure, and you take high blood pressure medication, some people get better. Some people improve a little bit. Some people don't improve at all. There's variance within a treatment group. That's within groups variability. Between groups variability is how much group 1 differs from group 2, differs from group 3 on average. Because remember, the claim that we're testing is whether if I give group 1 a different level of medication from group 2 and a different level of medication from group 3, that it will create changes in those groups, right? Those groups of people will start to deviate from one another. They will become different from one another along my dependent variable. So if that's the case, if the medication works, then I will have high between groups variability. However, if the medication does not work, I will have low between groups variability. So if the medication is functioning and working, I'll get a large F because the working medication creates differences between my groups, group 1 versus group 2 versus group 3, which will lead to high variance in my numerator. And then we're going to compare that to the variability within each group, the cumulative variability within each group. And we're going to hope that that variability is small, meaning that each group is homogeneous to itself. So if something looks like this image you see in front of you, group 1 versus group 2 versus group 3, this image would suggest a significant result because I have high between groups variability, right? Group 1 doesn't even overlap with group 2 and doesn't even come close to group 3, right? And group 2 doesn't overlap with group 1 at all. They overlap this teensy tiny bit with group 3, right? The 3 groups are dramatically different from one another. They don't overlap. This suggests that the medicine works because different levels of the medicine, different amounts of the medication create 3 different looking groups. So in this case, we would want to reject the null hypothesis. The medicine works. However, if we were to visualize our results and they look like this, then we're going to probably have a small F value because look how much the groups overlap, right? Group 1 overlaps a lot with group 2 and group 3, right? They're all overlapping with one another. if I told you that someone scored right here, you would have a difficult time figuring out who they are, which group they belong to, because the groups look similar to one another. And if our three groups look similar to one another, then what it means is that the medicine isn't working, because the medicine doesn't make them differ from each other. If the medicine works, then the 0 milligram group should be very different from the 10 milligram group, who should be very different from the 20 milligram group. That's what should happen if the medicine does something. But if our results look like this, if we have high within groups variability, right, within each of our three groups, so group 1 has high variability, group 2 has high variability, group 3 has high variability. If we have high within groups variability and very little between groups variability, then the medicine doesn't do anything. It doesn't make the groups different from one another. We'll get a small f, and we will fail to reject the null. So an ANOVA looks at three sources of this variability, really two sources, the within groups and the between groups, and those add together to be total variance. We'll go over these in more detail when we actually do the statistics. Again, a reminder about between versus within groups variability. Between groups is differences among the groups. Variability within groups variability is variability within each group. As we conduct these statistics, which we're going to do in the next video, we will basically be filling out this table. So let's sort of take a look at this and break down this table. We have our three sources of variability between, within, and those are going to add up to total. We will derive a degrees of freedom for each of these sources of variability. We will derive a sum of squares for each of these sources of variability. We'll divide sum of squares divided by degrees of freedom to produce a mean squared for each source of variability. And then we'll use these mean squares to produce our F statistic, our ANOVA statistic. So what we're going to do as we learn how to do this statistic by hand, we're going to take basically each of these cells of this chart in turn, and we're going to learn how to calculate and fill in the value of this cell. And then those values will just sort of generate our F statistic, which is what we need. Okay, so we're going to stop there. That's sort of the theory and the methods behind the one-way ANOVA. In the next set of lectures, in the next set of voiceover lectures, what I'll do is really break down two example research questions so that we can see what it looks like when an ANOVA is not significant, which will be our first research question. And then we'll see what it looks like when an ANOVA is significant, which will be our second research question. So if you need to go back and watch this again to sort of review the methods and the theory, I suggest you do so prior to looking at the next videos, which will cover the math. So when I do the math, I'm going to sort of assume that we all have some basic understanding of the theory. So if you don't quite understand this lecture, if you need to go back and review it again, I highly recommend you do so, because when we do the math and when I do the voiceover on the math, I'm going to assume that we're all familiar with this theory that we've just gone over. So thank you very much. Rewatch it if you need to, and I will see you next time for the math. Thanks, everybody.